All right, welcome back from spring break, everybody. So we are in section 4.5. This is the last section of content that's going to be covered on exam 3. Section 4.7, we'll talk about that one in just a little over a week, but that's going to start us into our last major topic of the semester. So we're starting in 4.5, talking about optimization. So optimization is one of the big applications of mathematics in calculus, particularly in derivatives, because we want to be able to maximize and minimize values in real-world contexts, and particularly in modeling contexts such as money, such as area, such as distance, those kinds of things. And we'll see a lot of examples today with those types of concepts. Okay, so to talk about optimization, we need to look at the procedure behind optimization. So in order to solve an applied optimization problem, first thing we need to do, of course, is understand the problem. But basically, when we say understand the problem, we really just mean make sure you understand what the question is asking for. Okay, what are the values that I'm trying to maximize or minimize? Kind of how am I going to set this up? Okay, then you want to draw a diagram when applicable, so if it's appropriate. Draw a diagram. This won't always be essential, but it can be very helpful, and we will see an example later on today that in particular you really need to draw a diagram to help understand it fully. 3 and 4 kind of go together, so you want to assign variables to any of the quantities that need to be maximized or minimized, and any of the other values that we encounter in the problem. And then we need to determine a function that we're going to be optimizing. So if we're trying to maximize or minimize volume, right, we're going to assign the variable v, right, if we're going to do volume, and then we're going to determine the volume function that goes along with it, that we can then optimize. So these two really go together. Then for step 5, we're going to eliminate all but one variable. So when we're trying to find the max or the min of a function, this requires us to take a derivative. All right, take the derivative, set it equal to 0, find the critical numbers, and then determine whether it's a max or a min, test it, right? But in order to take the derivative in the first place, you have to have a function of one variable. So we need to use some other piece of information to help us eliminate all but one of our variables. And then we get to step 6, and step 6 is kind of a catch-all here, but optimize the function. So we have our 3 parts here. So the primary thing here is this is where the calculation takes place. So we're finding the derivative, setting it equal to 0, getting those critical numbers, and then testing them to see if they are maxes or mins. And then we also need to look and make sure that it's an absolute max or min. Now, if it's the only critical point on its interval or on the entire function, then we don't have to worry about that because we know that it is going to be the absolute max or min. We've seen that in the past examples as well. So this section, that's pretty much it in terms of a lot of new information. So it talks on the next page here just a little bit about how to determine the critical numbers for how to find the absolute extrema for open intervals. Really, you just look at the long-run behavior, but if you're dealing with a function that only has one critical point to begin with, that is going to be an absolute extrema, regardless. So that's pretty much it for new information. Now let's look at just a bunch of examples that are going to help us really understand what's going on here. So first up, a farmer has 2,400 feet of fencing and wants to fence off a rectangular field that borders a straight river. He needs no fence along the river. What are the dimensions of the field that has the largest area? So the first thing we should notice is, what am I trying to optimize here? Well, we're trying to find the dimensions of the field that has the largest area. And the key word that we want to focus in on here is largest. Largest, that's kind of a qualifying word. It tells us I want the largest area. Another way of saying that is I want the maximum area. So we're trying to maximize area of a rectangular field. So basically you have a rectangle. So that should give us an idea of what the problem is going to start to turn into. So if you look here, they give you some samples, this is the scenario going on here. So we have our river in all three of these, and we have our rectangular fencing, and we don't know necessarily which one of these is going to maximize area. We just know that the lengths of each of these sides add up to 2,400, right? That's how much material he has to build the fences. So, and if you look, you can see, right, 220,000, 400,000, 700,000. So, based on these three scenarios, this one certainly looks like it would be the biggest of the three. However, we don't know if it's the biggest of all possible combinations of dimensions. So, we need to actually find that conclusively. And that's where the calculus is going to come in. So, we draw a diagram, right? So, we have our rectangular fencing bordering the river. The river needs no fence. And then they've already kind of assigned the variables for us here, but we're trying to maximize area. And we find area by taking length times width, right, for a rectangle. And they decided that the length was going to be x, the width would be y. And so that's fine. We don't need to change that. You could have used L and W, L and H if you want length and height, like whatever variables you like. It doesn't really matter. Okay. So these are our variables. Now we need to eliminate all but one variable and determine the domain of the resulting function. So right now we want to maximize this function, but we can't do that unless we can take its derivative. So we need to get rid of one of these variables. Now, in these types of problems, there's always going to be a value that we're trying to optimize, and then another value that we already know. And in this case, if we go back to the problem, we know that he has 2,400 feet of fencing. That's going to be the key. So we know that the perimeter, right, the region around the edge of this rectangle is going to add up to 2,400. So that means, if I look back at this diagram here, this length plus this length plus this length is going to add up to 2,400. So that's going to be 2x plus y is 2,400. Now, we can go ahead and pick one of the variables to solve for. I'm going to go ahead and solve for y, because if you solve for x, which is not wrong, but if you solve for x, you're going to get a fraction, because you're going to have to divide by the 2. So I like to avoid using the fraction, so I'm just going to divide by, I'm just going to subtract the 2x over. Now I can use this expression for y and substitute it back into this equation for area. So we're going to have area only in terms of x, and that's going to be x times y. And y is 2,400 minus 2x. And let's go ahead and distribute that x. So that's 2,400x minus 2x squared. It also asked us about the domain. This is a polynomial, so its domain is all real numbers, so no restrictions on this one. So now let's go ahead and perform the calculus on it, because this is the function now that we're trying to optimize in terms of one variable. So let's take its derivative. So a prime of x, that's going to be 2,400 minus 4x. Set that equal to 0 to get the critical points. That's 4x equals 2,400. So x equals 600. Okay, we test it either using the first derivative test or the second derivative test. to make sure that it is a max. So you check a point to the left, say even 0. That gives us a positive in the derivative. And then check a point to the right, say, 700, something round and easy. And that would give us a negative value out of the derivative. So the function goes from increasing to decreasing. So that means that it is, in fact, a maximum. And because it's the only critical point on the entire function on this interval on all real numbers, it must be the absolute maximum. So that means this is a good value for x, and then our y value, right? Because we saw y was 2400 minus 2x a little bit ago. So that's 2400 minus 2 times 600. So 2400 minus 1200, which is just another 1200. Okay. So these are the values that we get. So the question was asking us to find the dimensions that give the maximum area of the field. So with these modeling problems, you do always want to end with some form of conclusive statement. So let's go ahead and just put that statement in here. So we could say the maximum area occurs for a field that is 600 by 1200 feet. So the maximum area occurs for a field that is 600 by 1200 feet. All right. So let's look at another one. So an ordinary aluminum soda can is to be designed to have a volume of 12 ounces or 355 cubic centimeters. So let's just take a note of that right now. It has a volume of 355 cubic centimeters. We're trying to find the dimensions, so the radius and the height, that uses the least amount of material. So again, breaking that down, this is our qualifier word here, least. Least meaning minimum. So I want the minimum amount of material, and we already know about the volume. So that should help us set up our functions here. So understanding the problem, so here's our cans, and they're going to have a volume of 355 cubic centimeters, and we're trying to figure out what dimensions R and H are going to minimize the materials being used. So the materials being used, that's going to be, if you're talking geometrically, like how are we going to find this geometrically, that would be surface area. Okay, surface area talks about, right, the actual space on the outside of the can that's being covered here, so that's this whole thing. Okay, so that's what we're looking for. So for our functions, when we assign variables, well, S, we'll go ahead and use S for the surface area. Okay, so that's the materials, or the aluminum. And then we're also going to look at the volume. These are the two expressions, the first one that we need, and then the one that we know. All right, so in order to get the surface area, we need to set up the function, the equation for surface area of a cylinder, and that's going to be 2 pi RH, so that's the area around the sides of the can, plus the area of the top and bottom. Those are each circular, so that would be pi r squared, and there's two of them, right? One top and one bottom, so that would be 2 pi r squared. Okay, so that's going to be our formula for surface area. And now we need to eliminate all but one variable. So to eliminate, we need to use our other expression that we know. So that's going to be V, so the volume. So volume of a cylinder, that's going to be pi r squared H. And that we know is 355. Now we need to solve for one of these variables in order to eliminate it in S. Okay, so we can pick either r or h, but I think it's going to be easier if we solve for h here, because if I tried to solve for r, I'm going to have to take a square root, right, because of that square on top there. So let's solve for h. So divide both sides by pi r squared. So we get h is 355 over pi r squared. And now let's take this value for h and put that into our expression for the surface area. So this is going to be, so S of r, because everything's in terms of radius now, 2 pi r h, so h is 355 over pi r squared, and then plus 2 pi r squared. And let's simplify that a little bit. Okay, so you get a little bit of cancellation here. So pi with a pi and r with one of the r's down in the bottom. 2 times 355 is 710 over what's left is r plus 2 pi r squared. So this is our function for the surface area, right, for the amount of material that's being used. And in order to optimize this, right, or to minimize it, we need to take a derivative. So let's take the derivative of this function. So that's s prime of r. So using the power rule, so that's going to be negative 710 over r squared, and then plus 4 pi r. Okay, and then we set that equal to 0. Okay, now I'll add that negative term over to the other side, so that's going to give us 4 pi r equals 710 over r squared. Multiply both sides by r squared so we can get rid of the fraction. So that's 4 pi r cubed equals 710. So r cubed is going to be 710 over 4 pi. And then take the cube root. 710 and 4, by the way, have common factors in them of 2. So it's going to have a 2, and that's going to be a 355. So this gives us r equals the cube root of 355 over 2 pi. So this would be our value for r, and then we could test that, right? Just throw it on a number line. And if you wanted, if you wanted to actually find this as a decimal approximation, that would be fine. Right? Just do that, and then that'll give you, so that you know what to choose on the left and the right, or just pick numbers that are so far away. Like you could pick 0, right? Well, not in this case because 0 doesn't exist. You could pick 1, right, and then pick some larger value. But you would find that goes from negative to positive, so we go decreasing to increasing, which means that this one is a min. Okay, and it's the only critical point, so it's the absolute min. So that gives us the r value. Now we just need to get the h value. The h value was 355 over pi r squared. So that's 355 over pi r, and r again is this, squared. Now it's not going to look pretty, but it is going to be right. So that's the cube root of 355 over 2 pi, and that cube root, square it. And that's the value of h. So what this tells us is, so what we were looking for was these dimensions that minimize the amount of materials being used. So the dimensions of the can that minimizes materials are cube root of 355 over 2 pi centimeters by 355 over 2 times the cube root of 355 over 2 pi squared centimeters, which again looks really ugly, but that is the precise correct answer. If you wanted to put this into more understandable terms, just get the decimal approximation. That's 3.837 centimeters by approximately 7.674 centimeters. And that would give you a better idea of what is actually going on in this scenario. All right. Let's look at another one. So an oil pipeline will connect 2 points A and B that are on opposite sides of a straight river 100 meters wide. Okay, so before we keep going, this problem is going to be really challenging to understand unless we draw a diagram. So let's just start drawing that now. So an oil pipeline will connect 2 points A and B that are on opposite sides of a straight river 100 meters wide. So we have our straight river, and it's 100 meters wide, and we have a pipeline that's going to connect a point A and some point B that we don't know exactly where it is, so it's going to be down there somewhere. Point B is 120 meters downstream from the point D, which is directly opposite A. So the point D is directly opposite A and is 120 meters from point B. Okay. Part of the pipeline will run underwater from point A to point C on the opposite bank, and then along the ground from C to B. So what that says is somewhere between B and D, we will hit a point C. This is the point where the line is actually going to be run. So it could run straight to D and then all the way down to B, or it could run underwater all the way to B and then not go underground at all, or it could go somewhere in the middle and then go the rest of the way underground. So what we have here is our scenario. Suppose the cost per meter of running the pipeline along the ground is $1, while the cost per meter of running it underwater is $1.50. Find the location of the point C that will minimize the total cost of the pipeline. So we're trying to minimize cost here. So this means that we're going to need to look at the distance that it's taking and know whether or not it's going under the water or underground. So let's go ahead and identify what we need to know here. So I need the location of the point C. That's really what it's asking for ultimately. So I'm going to just label that X, right, that distance, which means if this distance from C to D is X, and this whole thing is 120, that means the remaining distance from B to C must be 120 minus X. All right, so just kind of labeling all of our points here. Okay, so that's our diagram. And then to assign variables, we're trying to find the cost, right? So, and that's the value that we're trying to minimize. Right? Minimize the value of the cost. All right. So determine a function for the quantity to be optimized. So for that cost. So I'm looking for cost, so C of x. So let's go back and look at the diagram here. So the cost of running it underwater is going to be $1.50. So $1.50 underwater. That distance is going to be this one right here from A to C. Now we can actually figure out what that is because we know this length and this one, and this is a right triangle. So let's go ahead and just find that really quickly. So that's going to be, so the length AC squared, that's going to be, so x squared plus 100 squared. So take the square root, you get square root of x squared plus 10,000. Okay, so that's the distance that it's covering under the water. So that's going to be $1.50 times the length, square root of x squared plus 10,000, plus $1 times the distance it covers under the ground. So $1 underground. So that's going to be this distance, whatever's left. And that we already found an expression for. That was 120 minus x. So we can go ahead and just put that in here. So 120 minus x. And notice the way that we set this up, step 5 now becomes unnecessary because we already have only one variable, right? It's just x in this case. So we can rewrite this, write it a little, spread it out a little more. So that's 1.5 times square root x squared plus 10,000 plus 1 times 120 minus 1 times x. And now for the last step, so optimize the function that it asks us to do. So let me just put the first part right here. So let's take the derivative. So the derivative of the square root function, that's going to be, so this is 1.5 over 2 root x squared plus 10,000 times the derivative of the inside, so the derivative of x squared plus 10,000, and that's just 2x, right, plus 0. Plus the derivative of 120 is 0, minus derivative of x is 1. So let's go ahead and kind of combine terms where we can. So let me do this on the next page here. So c prime, that's going to be 3x over 2 times the square root of x squared plus 10,000 minus 1. And then to find critical points, we set it equal to 0. Okay, so this is going to give us, so 3x equals 2 times square root of x squared plus 10,000. Let's go ahead and square everything, get rid of that square root. Okay, multiply that 4 in there. Combine the x squared terms, so that's just going to give us 5x squared equals 40,000. Divide by 5, we get x squared equals 8,000. And take the square root of that, we get x equals 40 root 5 is the fully simplified version of that. So now we do need to test it, right? It's the only critical point, but we get 40 root 5, check a point to the left, a point to the right, to make sure that it's going from, let's see, if we want we're trying to minimize cost, so we would be going negative to positive. So we pick our sample points, we go from negative to positive, and then that, in fact, does give us a minimum. So, what did this x value tell us? So if we go back and look, we see here that x was the distance downstream that the point C is. And that's really what the question was asking for, is how far downstream does point C need to be to minimize the cost? And this answers that question. So we can say the point C should be 40 root 5, which, if you wanted to approximate, is approximately 89.44 meters downstream to minimize cost. All right. So that gives us the distance that would minimize that cost. All right, let's look at one more. So suppose 1,200 cubic meters, actually that should be square meters. Oops. So that's 1,200 square meters of material is available to make a box with a square base and an open top. Find the dimensions that maximize the volume of the box. Okay, so let's draw the box. So here we have our box. It has a square base, so that means whatever dimensions I pick to be one side of the base, it's going to be the same for the other. So I'll call it x for both. And then the height can be whatever you want to call it. I'm going to call it y. So let's see, what do we have here? So it's asking us to find the dimensions that maximize volume. All right, so we're looking to maximize volume, and we already know about the amount of material that's available to us. So that's going to be the value that we already know. And I already established variables here, so x, that's going to be, right, length and height, or excuse me, length and width. So that's length and width, and then y is going to be the height. Okay, so now we need to create the functions that we're going to use. So we're trying to maximize volume, so we need the volume of a box. So the volume of the box, that's going to be, right, base times width times height, or length times width times height, so that's just x squared y. And then we already know the amount of material being used for the box, so that's just going to be surface area. So that's just area. And the area in question, well, you can't really see it here, but here we go. So, but here, the bottom of the box has an area of x squared. Each of the sides has an area of x times y, right? X times y, x times y. And the top is open, so there is no material being used for the top. So the area of this box is going to be x squared plus x times y, and 4 of them, right? So times 4. So this is going to be x squared plus 4xy, and that, we know, is 1,200. That's given to us in the problem. So now, eliminate all but one variable. So we have to choose in our volume equation over here, do we eliminate x or y? I can tell you the easier choice to go with here is going to be the y, because there's two x's in this expression. So that's going to be even harder to simplify if you try to do it that way. But solving for the y, we can do that fairly simply. So subtract the x squared over, so that's 4xy equals 1200 minus x squared. And divide away the 4x. That's going to be y equals, let's see, 1200 over 4, that's 300 over x, minus x over 4. Okay, so that's going to be our value for y. So now let's go ahead and get that volume equation set up in terms of x alone. So that's x squared times 300 over x minus x over 4. Simplify. So that's going to be 300x minus 1/4 x cubed. And now that's just a polynomial, so we can go ahead and differentiate that. So let's do that. Because again, we're trying to optimize this volume, or maximize this volume. So that's v prime of x, so that's just 300 minus 3/4 x squared. We set that equal to 0. And then this gives us, so 3/4 x squared equals 300. Multiply by the reciprocal of the 3/4, so that's multiplied by 4/3 to both sides. That's going to give us x squared equals 400. And that gives us a nice square root. It gives us x equals 20. So once we get x equals 20, we can test that just really quickly. So pick a point to the left and to the right, right? So pick 0, you get a positive. Pick, 21, right? Something smaller is easier, and you get a negative. You go from increasing to decreasing, which of course does verify that this is a maximum. So if that's the x, now we need the y. And we said y was 300 over x minus x over 4. So that's going to be 15 minus 5, which is 10. All right, so we got our x, we got our y, and that's what the question was asking for, right? The dimensions of the box that maximize its volume. So let's go ahead and state that here. So the dimensions of the box that maximize volume are 20 by 20 by 10 centimeters, right? Because the length and the width of the base are the same. That's x by x, so it's 20 by 20 by 10 centimeters. So those dimensions give us the maximum volume that this box can have. All right, so that brings us to the end of section 4.5 and the end of examinable content for exam 3, which is coming up next week. We'll talk more about that in the review coming up next class. But then we'll start into 4.7 and then into chapter 5, starting